Last lecture, we had just gotten to looking at this example. We're looking at a circuit driven by a DC power supply, 12 volts. It's got a resistor in it, 30 ohms. If that's all there were in the circuit, we would be back in chapter 26. But we've advanced beyond that, and we have these new gadgets. We have an inductor in here with inductance. And that means that the current passing through this circuit is going to be time dependent, and we can map out what that current looks like as a function of time. So there was this long list of items that we are solving for. So let's we can move through this pretty quickly. Again, it was right at the end of last lecture, but I feel like there's so much going on here that we should go ahead and carry out some of these calculations. So here's what the circuit looked like, and kind of the first thing that they'd ask us about and we went in and solved for was the time constant. We said more inductance slows this process down. More resistance actually means it will take a shorter time because we're not going to a very large current in any case. And so that time constant worked out to be 7.33 milliseconds. On my graph, this is the function that we're plotting, 7.33 milliseconds then is the amount of time at which the current has reached 63% of its asymptotic value. The asymptotic value here being given by V naught over R, which is 400 milliamps. Now they ask a bunch of questions about what's going on when 200 milliamps of current are running. So kind of at the halfway point in terms of current and 200 milliamps. And so for that, what we did was go through and use this equation to determine how much time has passed. Turns out it was 5.08 milliseconds. And we used that to, or the current amount, to get the voltage across the resistor. And then we took the I as a function of t equation and took a derivative. So I took a derivative of that and got I naught over the time constant, e to the minus t over the time constant. That gave 27.3 amperes per second of the rate of current change. From that, we were able to get the voltage across the inductor. And then finally, we calculated power. V times I for the resistor gave us 1.20 watts. And V times I for the inductor also gave us 1.20 watts. The current was the same in both components, and the voltage is the same. Now, I think what they ask about was in addition to what we've done here. So we've done this pretty thoroughly, but they also ask about at what rate is energy coming out of the battery. So let's think about what that would be. For the battery too, I can do V times I. So the voltage on the battery is 12 volts, and the current going through the battery would be the 200 milliamps. Remember, this is just a one-loop circuit. Everybody's got the same current. So if I take the 12 volts and multiply by the 200 milliamps, I am going to have 2.4 watts, 2.40 watts of power is the rate at which energy is going into the circuit. So it works. The battery is putting in 2.4 watts. 1.20 watts are in the resistor going into thermal energy. So resistors do that, right? They just take the energy and create heat. And so I'm not getting that energy back. The energy that's been lost through the resistor. So the resistor is taking out 1.20 watts. The inductor also is taking energy in at 1.20 watts. but the inductor is storing the energy. So the inductor is hanging on to that energy for a future use. So inductors are going to store the energy, same as capacitors, but the resistors are going to thermalize the energy. And that's how these different components work. If we had a capacitor in this, the capacitor would also be storing the energy. So yeah, so I can figure out the power of the battery at a particular instant. Now another thing they ask about, what is the amount of energy stored in the inductor? And I didn't get that written down either, but the formula for that, the energy stored in an inductor is 1/2 L times I squared. So I can take the 220 millihenries, multiply that by I squared, 0.2 times 0.2 times 0.22 times 1/2. And that will give me some number of joules of energy that has been stored so far in the inductor. So as the current is going up, that indicates to us more and more energy is being stored in the inductor. All right, good example. Spend some time with this. Make sure that you understand all of the details from that. Now, we're going to move on and look at some different circuits. And what we have here is what's called an LC circuit. And in an LC circuit, it's kind of traditional to leave the battery out. So I don't have a battery in this circuit. There's no battery, right? If you look for it, you're not going to find it in there. Instead of having a battery as an energy source, what we're going to do is we're going to pre-charge the capacitor. So instead of starting out with a capacitor with no charge on it, in the LC circuits, we start off with a charged capacitor. So in a problem, if I have a homework problem or on the midterms, there's going to be some way I can determine how much charge initially is on my capacitor. Now, imagine what's going to happen if we close the switch. Well, if I close the switch, that's going to provide a path for electrons to leave that plate and make their way over to the positive plate. Now there's a path by which the electrons can neutralize the charges that are built up here. So we'll get electrons everywhere in the circuit shifting, and every time an electron comes off from this plate, an electron over here steps onto the plate. One leaves, one steps in, and I have this long line of electrons slowly making their way through the circuit. Now those were electrons, and so we have to say, well, what direction is the current in? And the current's in the opposite direction to the direction of the electrons. All right, so we close the switch. Current begins to move. Now there's an inductor here, and the inductor is going to moderate changes in current. So it's not going to let the current all happen at once. It's going to slow down the process, so it takes a little bit of time in order to discharge the capacitor. Now what does happen is when the capacitor has fully discharged, there's still current going through the circuit. And because there's an inductor there, the inductor is going to say, wait, we don't want the current to drop off too fast. So the inductor will end up causing the current to continue to flow, and that will charge the capacitor with the reverse orientation. So think of this as a pendulum, right? I pull the pendulum back, here is equilibrium, I let go. If there's nothing in the circuit to take, or nothing in the pendulum, sorry, if there's nothing in the pendulum or the circuit to take energy out, when I get back to what looks like an equilibrium position, the pendulum's just going to continue through to the other side. So even though there's an equilibrium position, objects don't just go back to equilibrium and stop there. Well, the same thing's going to happen here. What will happen is current will continue to flow in the other direction until all of the energy once again is stored up in the capacitor, and then it will oscillate back the other way. Now, these slides keep talking about electromagnetic oscillations. I don't know how electromagnetic this is, but there certainly are oscillations of the current. The current is undergoing oscillations. Now, we're going to find out some of the energy actually does radiate away, because what I've got is I have accelerating charges. Anytime we have variable currents, we've got charges that are accelerating. Accelerating charges are going to radiate energy away. But for now, we're going to ignore that effect, and we're going to move on and talk a little bit more about the circuit. So how would I set up the mathematics to represent a circuit like this? And what we have is I've got an inductor. So the inductor has a voltage that's L, di dt, and di dt can be written as second time derivative of the charge. So if I take this L and bring it over to here, that's the voltage on the inductor, plus the voltage on the capacitor is Q over C, and there's no power source. So I'm going to put a 0 over on that side, and it says the voltage drop of the inductor plus the voltage drop of the capacitor have to add up to 0. There's no voltage boost. There's no battery around to maintain a voltage. Now, this is the same equation as for, well, simple harmonic motion. The solutions to this are sine and cosine functions. So what this is saying is that the charge on the capacitor will oscillate with time. The amount of charge on the capacitor is going to vary from one instant to the next. We don't have to include this extra phase, but we can. So we can always throw a little bit of phase in there and say that's a little arbitrary. The key feature here is that we have some sort of a sine or cosine function and show that there are oscillations and that the oscillations are harmonic. Now the frequency of those oscillations, again, if we go back and look at the solutions to our differential equation, the frequency of those is going to be given by 1 over LC square root. So the square root of 1 over LC, and where that's coming from is right here. So let's say that I have a charge that as a function of time behaves like a cosine. Well, if I take two derivatives, that's going to become negative the cosine, and the negative cosine has to cancel with the cosine function here. When I take two derivatives, I also bring out two factors of omega. And so those two factors of omega need to be equal to 1 over LC. And that's where this formula is coming from. So that's kind of interesting too. What we can do is we can control how rapidly this circuit oscillates back and forth. And that turns out to be very useful. If I'm building a transmitter, for example, and I want the transmitter, the cell phone or whatever, to transfer a signal at a particular frequency, I can use certain values of an inductance and certain values of a capacitance to make sure that the circuit is oscillating at a particular frequency. So I can use it as a tuner to sort out different signals from radio stations, from different communication devices. We can use this as a way to tune in to a particular frequency, and we can do that by determining what capacitance and what inductance we want to work from. Now, the current as well is sinusoidal. I always feel like they use the wrong, I don't like putting the minus sign here, but it works either way. It just depends on which direction you're going to call the positive direction for current. But let's go ahead and try this. So what it's saying is, let's think back about that capacitor. Remember the capacitor that was charged and then we had it hooked up to a circuit with an inductor, and we had a switch that was sitting there ready to close, and then we closed it. And when we closed that switch, the capacitor had already been pre-charged to some value, and we're going to call that value Q0. Now, since there's no resistance in the circuit, at least we're imagining this is a circuit with no resistance at all. If there's no resistance, we're not going to lose any energy. There's no resistance. We're ignoring radiative effects, where energy is radiated away as a signal, which would actually happen in an oscillating circuit. So if we ignore radiative effects, where we generate a bunch of electromagnetic, well, a bunch of photons coming off of the circuit, then the capacitor, as it goes through these cycles, will keep coming up to the very same value of Q0. So it'll discharge, completely discharge down to 0, but because of the presence of the inductor, the current continues. And as the current continues, it begins to charge in the opposite orientation. So this discharges all the way to 0, but then because of the inductor, it charges oppositely and completely charges to the same value of Q0, but with the reverse polarization. What was positive and negative is now negative and positive. And then the same thing happens. That's just half the cycle, and then we go back up to complete one cycle. So one cycle is right here. There is the period of the cycle, and we can get the period by taking 1 over the frequency. 1 over the frequency, f, frequency, is going to give us the period for that. So I could do a graph and write down exactly how much time it's taking for each one of the cycles that we're looking at. Now the current, the peak value of the current is going to be omega times Q0. Remember when we went from charge into current, we took a time derivative, and that time derivative brought out a factor of omega, and it says the amount of current that we have is going to be given by omega times Q0. And the current also is going to continue to reach the same peak values. And that's because there's nothing to take energy out of the circuit, so the current continues to oscillate with no reduction in the amount of the current. Now, they've got this divided up, each cycle divided up into, I guess, half cycles. So this is one complete cycle here. And they've got the half cycle right in the middle. That seems fine. It's also useful to think about 1/4 of the cycle. So at the very beginning, the capacitor is fully charged, but there's no current. When we first close the switch, there is no current because there's an inductor. And the inductor prevents the current from suddenly jumping to some other value. So we're seeing the effects of the inductor there. Now after 1/4 of a cycle, the capacitor has fully discharged, and now the current is at its maximum. All the energy now is stored in the inductor. At half a cycle, now the capacitor is fully charged, all of the energy is back in the capacitor, and there's no current. And then at 3/4 of a cycle, the capacitor has discharged, all the energy is back in the inductor, and then after a full cycle, we're right back where we started. Okay, so that's how we can separate or segment the cycles into 1/4. A series of 1/4 cycles is useful in kind of stepping through and seeing what's going on in the circuit at a particular instant in time. Now, if we do think about energy, and here are the energy formulas. So the total energy in the circuit, we're going to say, is given by the electric field energy in the capacitor plus the magnetic field energy in the inductor. And for the capacitor, we've worked with this formula before. 1/2 Q squared over C is going to tell us how much energy is stored in the capacitor at any particular instant. I just have to plug in a value for Q, and I can use that to determine how much energy is in the capacitor. In the inductor, the energy formula for an inductor is 1/2 L times I squared. So that's the amount of energy I have stored in the inductor. So those are my two energy formulas, capacitor, inductor. Now what we said is that the charge in the capacitor is varying like a cosine function. The current through the circuit is varying like a sine function. So what we can do is we can show that 1/2 Q naught squared over C is the same thing as 1/2 L I naught. And that means we can add the cosine squared and the sine squared portions of the energy, and that tells us at every instant the total energy is constant. So the total energy is this dashed line. And then I have a cosine squared function. The red line is showing how the energy in the capacitor varies as a function of time. And the blue line is showing how the energy in the inductor is varying as a function of time. If I add those two functions together, I get the steady, constant amount of energy in the system. So again, it's like a pendulum swinging back and forth, where we had kinetic energy and potential energy, and the total energy was constant at every instant. This time, it's two potential energies. It's the potential energy in the electric field of the capacitor and the potential energy in the magnetic field of the inductor. Now, if you notice, when we went through a full cycle, the capacitor would fully charge in one direction, and then it would fully charge in the other. That constituted a cycle. Now, during one complete cycle, what's going to happen in terms of energy is, well, during one complete cycle, the capacitor actually goes through two complete cycles in terms of energy. It doesn't make any difference in terms of energy whether the capacitor is charged plus, minus, or whether it's charged minus, plus. Both orientations of charge on the capacitor represent an energy peak. So I have an energy peak here, and then I have another energy peak here. Similarly for the inductor is going to go through two peaks in terms of energy. One with the current going in one direction, and one with the current going in the other direction. So you can imagine these circuits that oscillate, they're really handy. As we were saying, a lot of these are used in different communication devices to generate different frequency signals. So here's an example they've given us. So they've said, okay, fine, let's take a look at a particular circuit. Let's say that we have an LC circuit. It has no power supply. We're just going to work from the energy that has been initially stored in the capacitor. The capacitor is really low capacitance here. It's at 1200 picofarad, barely a nanofarad of capacitance. So they've picked something really low here. Let's see. It is connected to a power supply in order to charge it. And then at t equals 0, it is connected in a circuit and a switch is closed. So, oh, it's a 500, there we go. I was looking for the voltage on the power supply. So we use 500 volts. That's, you know, they're not kidding around here. 500 volts to charge this little tiny capacitance of 1200 picofarads. And then in the circuit, there will also be an inductor, and an inductor is going to have an inductance of 75 millihenries. So those are the values for capacitance, for inductance, and then you just want to know everything about the circuit. So, you know, we're getting used to doing this. They want to know what's the initial charge, what is going to be the maximum current, and what's going to be the frequency and period of the oscillation, and what's the total energy of the circuit. So they say the energy is oscillating. If you add up the capacitor and the inductor, what's the total amount of energy in the circuit? Let's see how we might go about solving all of those questions. There it is. There is our capacitor and our inductor that make up the LC circuit. And I should have put a couple of exclamation points here. There's no power supply. There's no battery. And so whatever energy is in the capacitor, that's it. That's all we have to work with, is whatever energy the capacitor brings with it. Now, the capacitor is at 1200 picofarads, and it says that we charged it using 500 volts. And so I did find out what the initial charge on the capacitor would be. It's going to be C times V, and that ended up giving us 600 nanocoulombs of charge. So that's how much charge we have initially. Now, I guess we could come down here, as long as we're looking at this, and say, well, how much energy is that? So we initially charge it at 600 nanocoulombs, and that's at a voltage of 500 volts. So the 600 nanocoulombs times the 500 volts gives us 150 microjoules. So that's it. That's all the energy we have to work with. That represents the total energy in the circuit. Now that energy is going to end up being transferred into the inductor and then back to the capacitor and back to the inductor and back. It's going to go back and forth, but at every instant, assuming no radiative loss, assuming zero resistance, we're always going to have 150 microjoules in the circuit. Let's take a look at a little more detail also with the differential equation that we are using. So what does the differential equation look like for this particular circuit? The differential equation looks like this. We say that there's no power supply, there's no battery, and so all we have are a couple of what we consider to be voltage drops. So the inductor is a voltage drop, the capacitor is a voltage drop. Now, that says that the voltage across the inductor is going to be represented as L di dt, and the voltage drop across the capacitor is given by 1 over C times Q. Now, what is this dq dt stuff? And I itself is dq dt, and that says that di dt is going to be the second time derivative with respect to charge. So taking this expression, substituting in my second derivative, I end up with dq dt, second derivative actually, second derivative of charge with respect to time as a function of time is going to be equal to 1 over, minus 1 over LC times Q. And this is the solution that we end up with. In order to convert back into current, I'm going to take dq dt. And so now I have an equation for the charge as a function of time, and I have an equation for current also as a function of time. Now when I took this derivative, a factor of omega came out. That says that I naught here is actually equal to Q naught times omega, and that's a way to go in and determine what's going to be the peak current in this particular setup. Also, what we find is that the 1 over LC is going to be equal to omega squared. So that lets me come in and figure out what the frequency will be for the circuit. Now, what I can see from the formula here is if I want a really high frequency, what I want to do is put a tiny amount of capacitance and a tiny amount of inductance into that circuit. Let's see why that works. Let's say we close the circuit. Charge begins to flow. We've got a current set up. What's going to determine how long until we've completely reversed the charge on the capacitor? If the capacitor has very little capacitance, well, it's not going to be storing much charge. Similarly, if the inductor doesn't have much inductance, then the current's going to happen pretty quickly. So if I want something with a really high frequency, I don't want much inductance and I don't want much capacitance. Now the flip side of that is, what if I want a really leisurely current change? You know, I want the frequency to be really small. I want a really long period for these oscillations. Well, if I want omega to go really small, then I turn up the inductance and I turn up the capacitance. If I got a great big capacitor and it's got all kinds of capacitance, that's a lot of charge that has to discharge. And if I've got a lot of inductance, that means that the inductor is going to make sure that the current doesn't change too quickly. So that combination gives me a really low frequency and a long time period. Now, let's plug the numbers in and see what we get. For omega, the frequency in terms of radians, that came in around 105,000 radians per second, and the frequency came in at 16,800 hertz. Again, check all these numbers. If you find any errors, let me know right away. So go ahead, not a problem. Let me know if there are any numerical errors that you have found in any of these example problems. Let's see. Oh, you know, they ask about period, and I never got that included. How would I get a period? Because I do like to include period in these kind of problems. I think that's an important thing to ask students on, say, midterms. Now, the period would come from taking 1 over the frequency. You know, if I've got frequencies of like, 16,800 hertz, the period's going to be a tiny fraction of a second, right? It's going to be it's going to be, I don't know, 20 or 30 microseconds. Check and see, check for yourself, see what the period turns out to be on that. So I think we got all the questions answered, and I hope along the way also conceptually it's making sense about what's going on. Why are we getting the values that we're getting? So let's just run back through this very quickly. Based on the voltage we used to initially charge the capacitor. Now, that battery is not here. So that was a separate circuit when we first charged the capacitor. We were able to bring the 600 nanocoulombs onto that capacitor, and then we plugged it into this circuit. The maximum current we're going to reach in this circuit is 63.2 milliamps, and that comes from Q naught times omega, and then that was the energy that was stored in the circuit. All right, questions on any of that? Again, no power supply. We could put a power supply in, but if we put a power supply in, it just complicates the circuits. So we're not going to do that. We're going to stick with just a straight LC circuit. All right, here we go. It's time to put an inductor and a capacitor and a resistor all together into the same circuit. Now, we're not going to put a battery in this one either, so what we're finding here is, well, it's kind of the same thing as before. What we're going to do is we're going to pre-charge the capacitor, we're going to close the switch, and then we're going to look and see what happens. Now, there's actually different possibilities here. In some sense, this LRC circuit is more realistic. When we only had an inductor and a capacitor, it's like saying, yeah, right, like there's no resistance in the circuit. What about the wires? What about the inductor and the capacitor themselves? Do they have any resistance in any of what they're built out of? So it's really unlikely you would have an idealized LC circuit. Now, on the other hand, this is actually probably pretty realistic. We can imagine building a circuit that has an inductor and a capacitor and some amount of resistance. Now, depending on how much resistance we have, this circuit is going to behave differently. One question we could ask is, are we still going to get those oscillations, right? When we had just a capacitor and just an inductor, we had oscillations. The current would go one way and then it would go back the other way and it would oscillate back and forth. Is it possible we're going to still see that sort of thing going on? And we will if the resistance is small. So as long as there's a threshold resistance below which we will continue to get oscillations. The oscillations slow down a bit because of the resistance, but not necessarily a lot. Again, as long as we stay below a certain threshold value for resistance, we will continue to get oscillations. Now, what happens if we put more resistance in? Well, if we cross the threshold in terms of resistance, what's going to happen is when we close the switch, the current begins to run, but instead of oscillating back and forth, it just comes back to equilibrium. Think of the pendulum example again. Let's say that I've got a pendulum, I pull it back, I let go, there's no resistance, there's no air resistance, for example. If there's no air resistance, then the pendulum just swings back and forth forever. What happens if now I put a little air resistance in? Well, then the pendulum slowly comes down and asymptotically reaches equilibrium. In that case, energy is being taken out of the system, and the amplitudes of those oscillations will asymptotically drop off. What would happen with a pendulum if we put lots of air resistance in? And once we cross a certain threshold, I let go of the pendulum, there is now so much resistance that it slows down and it never crosses the equilibrium position. That's what happens when we put enough resistance into this circuit. So if I stay below the threshold, I'll get those oscillations. The oscillations will be dying off. But if I put more resistance in, then the circuit will use up all of its energy in just returning to equilibrium. So those are predictions, again, from the mathematics. We can go into the lab and verify that's really what happens for different values of resistance. So let's see what this differential equation looks like. Now, we're getting to where we're getting some practice with these. We're getting some experience. And I guess at this point you could go, okay, how is this set up? And of course, as always, the first thing we want to do is get rid of their ridiculous period. They don't really put periods on equations in books, do they? Uh-oh, I got to go back and look. Anyway, I'm getting rid of that period. And the zero on this side is saying there's no battery. There is no consistent voltage boost driving this circuit. So what I do have is I've got an inductor, I've got a resistor, and I've got a capacitor. And this first term represents the voltage drop occurring with an inductor. Here is the voltage drop that occurs with a resistor, and here is a voltage drop that occurs with a capacitor. Now, dq dt, that's the same thing as current. So even though I'm writing it as dq dt, it's still R times I. It's still the voltage drop for a resistor. This is the second derivative of charge with respect to time. But remember, that's the same thing as di dt. So yeah, those are the formulas we've been working from. Now when you solve this differential equation, what you find is this. You find that the system will be what's called underdamped. Now damping is taking energy out, and underdamped means the energy, the rate at which we're taking energy out is insufficient to prevent oscillations. I guess that's the way you say it. Anyway, with the underdamped example, when R squared is less than 4L over C, we will continue to have oscillations. So we'll get these ever decreasing amplitude oscillations taking place. the threshold, if we cross the threshold where the resistance is greater, R squared is greater than 4L over C, then we have what's called overdamped. Overdamped means that we're taking the energy out so rapidly that the system just returns back to equilibrium. All the energy has been taken out. And then finally, you might ask, well, what happens if R squared is right at the threshold value? If it's right at the threshold value, we call that critical damping. And when we have critical damping, that's kind of the least abrupt way of coming back to equilibrium. Think shock absorbers. You don't want a shock absorber that's overdamped, so when you hit a bump, it's like there's no shock system at all. It's pretty rigid. You don't want a shock absorber that's underdamped so that the car oscillates for the next mile down the road. What you want something is critically damped. Critically damped takes that bump and as smoothly as possible returns the system back to equilibrium. So that's kind of what we're looking at or hoping for in this particular setup. Oh, here they are. Here they are all plotted out. So what we've got here is A is underdamped. That's where we continue to have oscillations. That's where there's a low amount of resistance below that threshold value that we were informed about. And then in B is overdamped. We're coming back to equilibrium and we're coming back fairly quickly. And then C is critically damped. And C is the smoothest, this stretched out manner in which we're coming back to equilibrium. So it's the least disruptive, I guess, in some sense. It's the one with where the changes are spread out the most. Now, a question comes up, well, if we are underdamped, let's say that we look at the example where there's not very much resistance, the system is underdamped, what is the frequency of oscillation going to be like? Now, if you remember, when there was no resistance at all, the frequency used to be 1 over LC square root. So it used to look like this. That used to be our formula for the frequency of oscillations. And now what they're doing is they're calling it omega prime. Once we introduce a little bit of resistance into this circuit, what we find is that the frequency goes down. Now the frequency going down means the period's a little longer than it used to be. That is the effect. So as we add more and more resistance, what happens to this formula is when R is equal to 0, we go back to a purely inductor capacitor circuit, and the frequency that's the highest frequency we would have. As we add more and more resistance, the frequency slows down, and eventually, if we increase the resistance right up to the critical amount, at the critical value of resistance, then R squared over 4L squared equals 1 over LC, and the argument within the square root sign goes to 0. And that says the frequency has slowed down entirely to 0, and at that point we're critically damped. So no longer do we have those oscillations. All right, when we look at what's happening in terms of charge on the capacitor. So if we use the charge on the capacitor as a way to kind of monitor what's happening in our circuit, what we find is we still have, in the underdamped case, we still have oscillations. So the cosine omega t, that is still there. Now, we've replaced omega with omega prime because we do want to take into account the reduced frequency due to the presence of the resistor. So it becomes cosine omega prime times t. We still have the Q naught, But what's new, what's kind of the biggest new part, is that now we have an exponential factor, an exponential drop-off factor, which is e to the minus t over a time constant. So there's a time constant in there. And what that's saying is that, let's see, when t is equal to 0, and again, I'm going to ignore this phase factor. When t is equal to 0, this goes to 1, and this goes to 1, and at t equals 0, q is equal to q naught. So I guess by definition, we really do need to get rid of that phase factor. All right. As time goes on, this factor is going to steadily decrease, and that says, during the first cycle, we're not going to come back to the same amount of charge. The capacitor will never be fully charged again because we're losing a little energy due to the presence of the resistor. Okay, so this ends up modeling, describing what's going on with the charge in the capacitor. Now here's an example, so we can go through this. It's kind of interesting. They're calling it LC oscillations with resistance. So LRC circuit, I guess that means underdamped. So we're saying it's got some resistance, but the oscillations are still happening, and that means that it's underdamped. At t equals 0, we're going to start with a charged capacitor. Now the capacitance value, 4.8 microfarad, the resistance is 3 ohms, and the inductance is 40 millihenries. And I guess the first question that we need to answer, and I think it's the first question they talk about, is it underdamped or overdamped or critically damped? They seem to be suggesting it's underdamped, but we better check and make sure. So the first thing they want us to show is the circuit going to oscillate or not? So we got to show how much damping there is. And then, they do say, find the frequency, so I'm guessing it's going to be underdamped. And then they say, what is the time required for the charge amplitude to drop to half of the starting value? And then finally, what value of R would make the circuit non-oscillating. I thought it said no oscillating, but it's actually just non-oscillating. No. All right, here's that problem. And again, there's a good number of details here. We'll try and step through everything very carefully. You should do the same when you're going back over each of these examples that we have looked at. Make sure you understand each step. If there's any questions, just contact me, contact me in some way. Email, office hours, whichever. So here's our RLC circuit. And again, there's no power supply. We're starting with a capacitor that has been charged, and we're going to use that as our energy source. Now, the function that we're going to use to keep track of the charge is, here's my starting charge on the capacitor, here is the exponential drop-off, and here is the oscillating factor. Now, the time constant is given by 2L over R. That was something they showed us. They didn't really go through and derive that, show us where it came from, but the time constant for these circuits will be 2L over R. Let's see what that gives us. L is 40 millihenries, R is 3 ohms, the capacitance 4.8 microfarads. I plugged those in, and what I got was 26.7 milliseconds. So that's telling me the time constant for the drop-off. Now, what's going to be happening then if I graph Q as a function of time? So it's this graph right there. The Q is going to start off at Q naught, and then we're going to have these oscillations take place. But as you can see, the oscillations are going to be decreasing in terms of their amplitude, and that decrease is going to occur within an envelope, an exponentially decreasing envelope. So the envelope, the oscillations are going to stay within the envelope as we've defined. So the way we think about this is, well, the cosine factor, cosines can vary between +1 and -1. And so the Q at any instant will never be larger than Q naught e to the minus t over tau, and that's why that becomes an envelope, a limit, in which the oscillations are taking place. Now we've determined how that envelope is dropping off. It's dropping off with a time constant of 26.7 milliseconds. So I can look to see where this has dropped to 37%, you know, and right there, one time constant has gone by. Now what I might want to think about then is, well, if one time constant has gone by, how many cycles have we gone through? That's kind of a separate question. So let's take a look and see how we can determine how many time constants we may have gone through. To determine the number of time constants, let's do this. Here are the oscillations that are taking place, the oscillation frequency. This omega is given by 1 over LC minus r squared over 4l squared square root. It's a lot to keep track of. I know some of these calculations that we've been looking at, especially in chapters 29, 30, step through them carefully. Just the calculations themselves, make sure you're not losing track of units. Make sure that you're not losing track of the calculations themselves, the numerical portion. Okay, that said, I hope everything I've calculated here is accurate. Anyway, I got a frequency of 2280 radians per second, and that's telling me that the frequency is 363 hertz. Now, if the frequency is 363 hertz, then the period of each oscillation is 2.75 milliseconds. So I put that up with the time constant. So I got a time constant that's 27 milliseconds, and I've got a period that's 2.7 milliseconds. And what that tells me is I didn't really scale this very well when I drew it. So let's think, how should I have drawn this to better represent what's going on? And what this is saying is, during one time constant, I should be going through about 10 cycles. This is about 1/10 the value of this. So again, the idea would be to fit maybe 10 cycles in here instead of 2 or 3. Now, I didn't draw it carefully. I apologize. I was aware of that. I didn't draw it as carefully as I should have. So again, I've got like 10 cycles going on inside here during the time when one time constant goes by. So I wrote that. There you go. 10 oscillations per time constant. And that's not what the graph looks like. Now, what that says then, let's see, we maybe are going to come back and answer this. I think this very first part of the question, I never got it answered, so I guess we should do this first. It said this. It said that in order to even have oscillations, in order for the oscillations even to occur, R needs to be less than 4L over C square root. So I checked it. So 4L over C square root, I plugged all the numbers in, and that becomes 183 ohms. So now it's not really a resistance, but just the values of inductance and capacitance are giving me a reference amount of resistance. It's setting the threshold. So it says, given this amount of inductance and this amount of capacitance, what is the resistance threshold below which we will continue to have oscillations? So in order to have oscillations, we need to have the resistance below 183 ohms. How did we do? We did pretty well. That's pretty minuscule, right? So the resistance that we've put into this circuit is nowhere near the threshold. We could have put in, another 183 ohms. In any case, what that's telling us is the frequency of the oscillations is going to be just very minimally affected. It's not going to make much difference at all. The energy is going to be coming out pretty slowly. So anyway, that's kind of what we're looking at with this. So I got the oscillation frequencies calculated. We established that there will be oscillations. I guess the last item on our list of things to calculate is how much time is it going to be until the charge has reached 1/2 of its original value. Now there's a couple different ways of interpreting that, and so I want to be clear, there's two different ways you could think about this. Let's see. Clearly, during the very first cycle, the charge drops all the way to 0. So it could be that what they're asking us about is at what point during that first cycle does the charge drop to 0? But that's typically not what the questions are after. Typically what they're after is, when does the envelope itself drop to 1/2 of the original value? So that's what I'm going to solve for. Now, the argument for that is, sure, the current drops to 1/2 of its value, but then it comes right back up. And then it comes right back up again, and it comes right back up again. So I didn't solve for the first cycle. I solved for the envelope itself drops to 1/2 of its value. I could have done both. Probably would have been a good idea. In any case, what I can do then is I can take this expression right there and say, when does e to the minus t over tau drop to 1/2? When that drops to 1/2, then that envelope that limits the amount of charge we're going to see on that next oscillation of the capacitor is dropped to 1/2. So I set that equal to 1/2. Again, I solved this equation for t and got the time constant times the ln of 2. I took the time constant, multiplied it by the ln of 2, and I got 18.5 milliseconds. So past that time, past the time of 18.5 milliseconds, that capacitor is never going to come back to 1/2 of its original charge again. That's the last time at which half of its original charge is still a possibility. Beyond that point, there's enough energy gone from the circuit that we'll never be charging the capacitor back up above that value. All right. Now, one thing that's missing here, which we could have included, which I probably would have liked to include, is we never really asked what the Q naught is, right? What was the original Q naught? We don't know. They could have told us that, or they could have told us how the capacitor was initially charged. They didn't, but then they didn't ask anything that required us to know either. So, all right, also a good example, you can see these circuits are getting more complex. So as far as DC circuits and circuits without power supplies, we're kind of through that. Your next look at DC circuits will probably be in a circuits class or something. Now we still have AC circuits. We haven't touched circuits that are driven by an AC power supply, and that's actually what we're going to spend a good amount of time looking at for the rest of this chapter. Okay, so here they are. Here's a circuit with an AC power supply. So here is what we draw for the AC power supply, and here is a resistor. We're going to start off with a very simple circuit. We actually looked at circuits just like this back in chapter 25, but now we want to make the circuits a little more complicated. So we're going to start off with resistors, but pretty soon we're going to be adding other things in there. This is just kind of a reference for us. So it says this. It says that when we start driving this circuit as an AC circuit, that the resistors, capacitors, inductors, they have different voltage relationships. And so we're going to take a look and see how that works. Now, you might be thinking, well, didn't we already look at oscillating circuits, and didn't they have different phase relationships? They did. And so we've already looked at some of those examples without any power supply at all. But now what we're going to be doing is using a power supply to kind of back up, provide an energy source. So when we start to lose energy because of the resistor, we can continue to have the circuit operate instead of just the current gradually disappearing. All right, let's write in some formulas for this. Now, as a reference, what we're going to use is the current is equal to I naught, some peak value, times the cosine of omega t. And so that is coming from the idea that the voltage is also behaving like a cosine function, and that I can get the current by taking the voltage and dividing through by the resistance. So everything works the same way it did back in chapter 25. Now on the graph here, what they're doing is they're showing a cycle and a half or something, and they're showing the voltage going through one cycle here. They're showing the current going through one cycle. We're representing both functions by a cosine function, representing both quantities by a cosine function. And on the vertical axis, we're superimposing two different graphs. And so what they've done is they're showing voltage and current. It's really two different graphs. Since current and voltage have different units, they can't really be compared. Like, I can't say there's more voltage than there is current. This doesn't make any sense. It's like saying, you know, that there's more kilograms than there are meters. It's not a useful comparison. So anyway, the reason that these are both on the same graph is to show that they're both sinusoidal, they're both being represented by a harmonic function, and that those harmonic functions are directly in phase with each other. So the voltage and the current are going to be right in phase. And the reason we're making such a big deal about this is because that's not going to be true for the capacitor. It's not going to be true for the inductor. Only the resistor has this simple phase relationship between the voltage and the current. Now, what would happen with an inductor? So now I've taken the resistor out, I've replaced it with an inductor, and it turns out that when we're analyzing AC circuits that are powered by an AC power supply, we don't need any resistance. We can actually work exclusively in terms of inductance. And the reason for that is this. If, let's go back and ask a couple questions here. So here I was with my AC power supply. What that's going to do is it's going to drive current in one direction and then drive current back in the other direction and then drive current this way and then drive it this way. That says there's going to be a group of electrons in the resistor that are just going back and forth all the time. This is going to be putting energy into the circuit, and those electrons that are in this resistor going back and forth, they are going to be converting their energy into thermal energy. They're going to be running into things. So those electrons are going to be bumping into the resistor molecules, and they're going to be transferring their energy, and that resistor is going to heat up. And it doesn't matter which way the current's going, the energy is going to be dissipated into heat in that resistor. Now when we think about an inductor, inductors like nice, steady currents. But we've hooked it up to an AC power supply. So this is like the inductor's worst nightmare, right? It's like, oh no, the current is constantly changing. First of all, it goes one way and then it goes the other way. And so what the inductor is going to do is it's going to try and prevent all of these current changes. It's going to try and minimize the rate at which current goes here and then minimize the increase in that direction. And as a result, the inductor is going to have basically a resistance. The inductor itself is going to limit the amount of current in the circuit. So the inductor becomes a current limiter, and it has a property now that's equivalent to the resistance of a resistor. So that's kind of interesting. The way we can think about this is, now remember the current, or the current that we had, let's step back. The reference that we're working from here is to say that the current is behaving like a cosine function. Well, if the current's behaving like a cosine, what is d I dt behaving like? And the reason I ask that is because the voltage across an inductor depends on d I dt. Now, if the current's varying like a cosine, then d I dt is going to behave like negative sine. It's going to behave like the time derivative, and that says that the voltage across the inductor is going to behave like minus omega. That comes from right here. So here is my current formula, and if I take a derivative of that, I'm going to get omega times I naught sine omega t with a minus sign out front. And then the voltage formula also has a factor of L, and that's going to be right here. So that tells me that the voltage across an inductor varies like negative sine omega t. So if we take a look at the inductor and ask, okay, here was our current. Now the current hasn't changed. Remember, there's only one loop that we're looking at. We're using the current as a reference, and we're always going to refer to the current as behaving like cosine omega t, at least for the explanations that we're going to work through in this chapter. That becomes kind of our reference. Well, if the current is behaving like cosine, the voltage is behaving like negative the sine. Sines are 90 degrees out of phase with a cosine. So whereas a cosine function, if I look at one cycle of cosine, it looks like that, right? The cycle ends right there. A negative sine function, well, it's going to be the mirror image of a sine function. It's going to look like this. So look at that. When the current is at its peak, there's actually no voltage drop across the inductor. But when the current is rapidly changing, see how the current levels off so that there's just for an instant, there's no change in the current, and the inductor can relax and be happy, but only for an instant, because then the current begins to change, and it changes more and more rapidly, and it's most rapid right there, and that's when the inductor is creating the largest voltage drop. The inductor is doing its best to prevent the current from changing too fast, and so the voltage ends up out of phase with the current in an inductor. So that's the key feature that we're trying to come up with here. So this is probably a pretty good place to pause, and so we'll stop for the day here, and then we'll pick up, and again, kind of the rest of this chapter, we're going to be looking at AC power supplies, driving circuits with resistors, inductors, and capacitors.